Okay, again, I encourage you to look through the notes and look through the video. I put videos for the week. I should have put it as a different link, but you'll just have to dig over here. So the video for the week has Tuesdays, last week's Tuesday's video, last week Thursday's video, and then that extra video that I included to make that correction from Thursday's lecture. Okay, today we're going to go over the next section, which is trying to solve for, what was the last section that we went over? 4.6, and 4.6 covered, what's it called? 4.7, and that was Cauchy-Euler differential equations.
The difference between the
Cauchy?
Cauchy-Euler like equation is like when you find m, it's not e to the x m.
Right.
Right.
It's x
x
to the m. Yeah.
How do we know which one to use? How do we know which one to use? Is it just like distinguish?
Well, let's see if we can do a quick summary. So if your differential equation looks like this, a y double prime plus b y prime plus c equal to 0, then this is the auxiliary equation business. So this is homogeneous. It has constant coefficients, which is nice. And we assume that your solution is y is equal to e to the mx. And then your auxiliary equation is taken directly from here. A m squared plus bm plus c equal to 0. And then from here you get, three possibilities. You got two distinct real roots, one repeated root or complex conjugates, and then your solutions, or whatever your solutions are going to be. So you're going to get your fundamental solutions, y1 and y2, and hopefully they're linearly independent. And if they're not, we got ways to work around that. The next thing we went over was the non-homogeneous one. So how do we do this? We set up the homogeneous part. And then we're going to get our y1 plus y2, or not plus, our y1 and y2 are fundamental solutions. And then depending on what type of function this is, if it's an easy function, we can use undetermined coefficients. If it's a more difficult function, then we're going to use variation of parameters. Undetermined coefficients or variation of parameters. And so the undetermined coefficients is when it's e to the x, when it's a polynomial, or when it's sine and cosine. When it gets more complicated than that, like tangents and some other weird stuff, then use variation of parameters. Okay, and the variation of parameters uses the Wronskian and all that business. Okay, so this homogeneous part is pretty much the same as the setup for the left-hand side of the differential equation is it's a linear differential equation with constant coefficients. And when we have constant coefficients, it usually turns out a little bit nicer, easier to work with. And then from there, we introduce the Cauchy-Euler equations. And the Cauchy-Euler equations have matching powers with a thing, with a whatever. So we got ax squared y double prime plus bx y prime plus c times y. And we started off solving for this when it's set equal to 0. So again, we start off with the homogeneous part. And then this time we assume that y is equal to x to the m. And in your auxiliary equation, you get your auxiliary equation by putting in the values. Now, I'm afraid to kind of think about this off the top of my head, but let me write something down, and I'm probably going to erase it because it's probably not correct. Auxiliary equation, who knows, it might be correct. am squared plus b minus a times m plus c equal to 0. I think that's the auxiliary equation. So I'll temporarily leave it here, and then when we do a problem, we'll see if it's correct, and I might come back and erase it. But in any case, what you would do is you would take your guess of an answer, which is x squared, or x to the m, and then you take a couple of derivatives, you put it into your equation, and then you solve for it, and then that's when you get your auxiliary equation. But in this case, you get your solutions based on whether you have two distinct roots, and in which case it's just x to the m, x to the m1, x to the m2. If it's repeated roots, remember we introduced the ln of x for this one, and if it's complex conjugates, then there's this weird, sine and cosine of something times ln x or something like that. So we have that in our notes somewhere, but it looks pretty different from our original one, but yet it kind of looks the same. There's a lot of similarities in there, right? Because it's working really close to it. But the point is to get your fundamental solution. And then when we throw in your right-hand side and make this into a non-homogeneous, then we do the same thing starting off over here. We solve the homogeneous counterpart. To get y1 and y2, your fundamental solutions. And then this time we don't have much of a choice. We're going to go directly into the variation of parameters. And this is where you have to remember when you do use a variation of parameters that you need to write this, and this is the mistake that I made in the video or in the lecture, was to make sure that you write this in standard form, which means you divide by the leading coefficient. And when I say coefficient, I mean the coefficient function with an x in it. So you divide by that, and you get b over ax, because the x's will cancel. And then here you have c over ax squared. More importantly, this thing, g of x divided by ax squared, that's the one that you use for your modified Wronskians in the variation of parameters. Okay?
What do you use to correct this type of differential equations?
Oh, we'll see it in the next chapter. Springs, and springs. You guys have seen those springs, right? At least the drawing of a spring hanging down. And so what happens is that you have a spring, you pull it down, you let it go, and then it oscillates. And so depending on the friction, those are the simple coefficients here. Now, if on that spring that you let go, that mass that you let go that's moving back and forth or up and down, if you attach a motor to it so that it actually has a certain movement, that's an external force, so that's what makes it non-homogeneous. And we'll see this, and we'll put these pieces together next time when we get to the next chapter. All right, so that's the rundown. And I'm hoping that you guys got a handle on this, because your quiz on Thursday will have something like this. Right? Okay. All right. So the next thing to talk about is that is to do an initial value problem. So in all these examples, we've found our general solution answer, and we have C1 and C2 floating around, and just say, okay, that's all good, we're done. But now let's see if we can include the initial conditions to make an initial value problem out of it. Have you guys had any of those in your homework assignments lately? Initial conditions? Solve for C1 and C2? You haven't done your homework.
What I did last Sunday. They were really long.
Yeah, so this is going to take longer now.
Oh my god. The board that we have is just seriously, it took me like an hour and to do one problem because it was a lot of product rule. Yeah, and I kept messing it up because it's either e to the x or e to the 3x and then 3x,
So,
e to the 3x, blah, blah, blah.
so this stuff right here, you know, you can say, oh, it takes a really long time. It takes half a page or a quarter of a page or, you know, a whole page. And so this is Chapter 4. Chapter 5, we're going to talk about some applications, and then we're going to squeeze that in as part of the test that you guys are going to take in a couple of weeks. But when we get to Chapter 6, we're going to start talking about series. And that is going to take you a long time. So one problem will take about 45 minutes to an hour, and it'll take about a page and a half to 2 pages and stuff. Yeah, for one problem. So don't complain yet. Wait till you start doing series. All right, let's see if we can do this problem. This is a Cauchy-Euler differential equation. It is homogeneous, set equal to 0. It has initial conditions, so I would call this an IVP. It's a second order, so I should expect 2 initial conditions for me to completely solve for this. And yeah, I think that's about it. All right, so this is the point where we assume that your solution is y is equal to x to the m power. Now, before I do that, since I wrote down the thing that I said I might erase, let's see if this is actually correct. So based on what I had written down earlier, my auxiliary equation should look like this. The a is equal to 1, and then the b is equal to 3, so it's 3 minus 1, and then the c is equal to 0. So my auxiliary equation should look like this, right? Based on what I wrote here. It's a times m squared plus b minus a times m plus c. Okay, let's see if that's actually correct. It is? Well, then I was right. All right, so is this good? Are we right? Should we check? Yeah. Yeah, check, or yeah, right? Yeah, check. Okay. So if I were to check, this is how I would do it. X to the m, y prime is equal to m, x to the m minus 1, and y double prime is equal to m minus 1, x to the m minus 2. And then I would put that into my differential equation. I have x squared, and then that big one, the y double prime, is this big mess over here. m minus 1, x to the m minus 2. So that's y double prime. And then I have a 3x times y prime, which is m, x to the m minus 1. And then I don't have a y, so I don't need to use this y. And this is set equal to 0. So, like always, we are going to be able to factor out an x to the m power. And so I have m times m minus 1. I already factored out all the x's. Plus 3m, again, factor out the x's. And then if I want to get rid of the x to the m, because we don't need to worry about that, I have m squared minus m plus 3 m, or m squared plus 2m. If you know the formula, you guys have a sheet of notes, you can just write it down. Yeah, so if you have that formula handy, all this step over here really goes to that. Or if I use my little thought bubble notation. All right, so we got the auxiliary equation, and we solve for the auxiliary equation. We can factor out. You have to be careful about this. Little things can go wrong here, and this is the part where it's really just algebra. But if you're not careful with your algebra, then you're off by a negative sign. Some of those integrals get kind of crazy and different. So I got m is equal to 0 or m is equal to negative 2. So my two solutions is x to the 0 and x to the negative 2. Okay. Oh, it's a homogeneous differential equation, so I could just solve for. I was going to go on and start doing variation of parameters, and then this is 0. So, wow, we're almost done. So your solution would initially look like this. So C1 times 1 plus C2 times 1 over x squared. And so what you want to do is you want to put in the initial conditions at this point. It looks like we're going to need to take a derivative to use a second initial condition. So let's do that here. I have 0 plus, this looks like a negative C1 or C2 divided by x, right? X to the negative 2. No. Negative 2 over x to the negative 3, or times x to the negative 3. Maybe you should check that. Is that right? All right. Okay. So let's put in our initial conditions where x is equal to 1 and y is equal to 0 according to this one, and y prime is equal to 4 according to the second one. So when x is equal to 1, I have C1 plus C2. That's supposed to equal to 0. And when x is equal to 1 for the second one, I have negative 2C2 over 1 is equal to 4. So my C2 is equal to negative 2. And according to that, my C1 should equal to positive 2. That's it. So I'm not going to put general solution. I usually put general solution with a C1 and C2, but this is a solution to an IVP, and I have already solved for C1 and C2. So I'm just going to say solution y is equal to C1 is 2, and then C2 is negative. Oh, but there's a negative. No, there's not a negative. So minus 2 times 1 over x squared. Yeah?
X, oh, wait, never mind.
The power, you mean?
Yeah, I was thinking of what you
Yeah.
y, if y is negative 1, then it's what y of negative 1.
Yeah, it's y a positive 1. So I hope that's right. Let's just say it's right. Okay, so as we can see, the homogeneous type of differential equation here is fairly easy to find your C1 and C2. When it comes to the non-homogeneous differential equation, it gets a little bit more difficult, and it gets a little bit more tricky. And so I don't know if I should start doing a problem and then redo it again. Well, I'm just going to go through the Green's function, which is our next topic. So if you have a homogeneous differential equation, initial value problem, the process should still be okay. You just, you find your general solution, and then you plug in your initial conditions and solve for the arbitrary constants, and then you would be done. Okay. So that's not a problem. The issue happens when you have a non-zero, when you have a non-homogeneous differential equation. So that's going to be our task, is to solve for non-homogeneous differential equations. And for this, we're going to use, essentially going to use variation of parameters And the variation of parameters is going to be written a little bit more compactly, compact, more compact, by introducing this function called Green's function. And Green's function is really that W1 and W2 put together. So let's take a look at how Green's function is introduced. So I want to put a header up here before we go on. So this is solving for non-homogeneous differential equations, or non-homogeneous, let's just say IVP, initial value problem. So that's a differential equation coupled up with your initial conditions. So what we have is a differential equation with a right-hand side, a non-zero right-hand side, and through variation of parameters, we're able to find what we call the particular solution. And the particular solution is it's the fundamental solution, and each of those times a u1 and u2 function. And the u1 function comes from the Wronskian. And notice the numerator doesn't look like the Wronskian, but it actually is exactly that modified Wronskian. So if we write down the modified Wronskian W1, remember W1, it keeps the second column the same. That's Y2 and Y2 prime. And then it has 0 and the F function over here. So when you find the determinant of this, you're going to get 0 minus, and then you get Y2 and F. And so that's exactly what's in the numerator of this function. Okay. Similarly, for this, if you do that Wronskian, the second modified Wronskian, find the determinant of that, it's going to be this thing minus 0, and so that disappears also, and then this is really what you have. And W is the original Wronskian. So now, their idea is, why don't we make this a function of, because we need to integrate this, right? So why don't we make this a function of t and integrate this with respect to t, and then put the x in, so that we'll have a complete list. So the second part of this comes in as an integral, because that's the step that we want to take. We want to integrate it. So to get y of p, this is what you're looking at. Now they're integrating from x naught, some random value x naught, which we'll see it's not all that random. It's going to be the x naught from your initial condition, to some variable x. Now x is a variable, so this is where you have to be really careful about your variables. The t is the variable that you're using to integrate, and then the x is an x variable that's going to be part of your solution. So what we did was just replace the u1 and the u2 with the antiderivatives of these things. And then just for kicks, we're going to take the y1 and put it inside of the integral. And notice that this is an x already. So that means with respect to this integral, this is an integral with respect to t, this is going to be constant. So whether that goes inside of the integral or outside of the integral doesn't matter, shouldn't matter, right? So right now it's outside. Mr. Green said put it inside. So we'll do the same for both. They have a common denominator of w. Oh, they also have this in common, f of t. So we can think about factoring that out. So now we have Green's function. So if we factor out the f of t, and then we put this y1x, Green's function is actually a function of two variables, x and the y, or x and the t. The x is your final answer variable. The t is going to be a dummy variable that's going to be used when we do our integrals. And so w, actually this was initially written as w up here, but conceivably, when we take the Wronskian, we'll have a function of t, right? So we should modify that to make it w of t. And then, again, we factor out an f of t outside. And if we just focus on this part of that integral, this is known as Green's function. So finally, we can rewrite the y sub p, instead of rewriting it as this long integral, we can write it a little bit more compact. Uh-oh. Moved the wrong one. So this y sub p, instead of writing it as a couple of integrals, or even worse, instead of writing it as y1, u1, y2, u2, and then figure out what your y's and u's are, instead of writing it as that, or instead of writing it as two separate integrals, we can make this more compactly, write this more compactly, and then really all you have is Green's function times f of t, whatever your f of t is. Okay? So that is our task, is now to write it like that. All right, so let's do an example. There's other theories behind this. The x naught comes from the initial condition that we have. So let's see if we can find a summary for this. So our task is to solve for an initial value problem. And if your initial value problem looks like this, and we're going to stay with the second order differential equation here. And you're given a I didn't put YP. I'll rewrite YP. But you're given initial conditions with x naught as your independent value. And then your y value is either y naught or y1 for the first or the original function in the first derivative. Then your solution is equal to this. So you're going to solve for the constants y sub c1 and c2 for this first part. And so remember that in solving for these things, we first solve for the homogeneous differential equation where it's set equal to 0. And that's pretty much how we're going to find our unknown constants c1 and c2 by plugging in these initial conditions, the exact same initial conditions as that. The tricky part is that your particular solution that you're going to get from variations of parameter slash Green's function, because we're just going to jump into Green's function, is going to be obtained by assuming that your initial conditions have the same x naught value, but then the outputs are 0. Okay? And that could kind of make sense because we're doing the superposition principle. You were stringing them together or taking your initial conditions, using them on the homogeneous differential equation, and then for the particular solution, they're not going to contribute anything else. So that's why we have zeros for that. We assume that it's equal to 0. And then I should write down here, it was in the previous page, but you should write down here that your y sub p is actually the integral from x naught, that same x naught over here, to the variable x of Green's function times f of t. Okay? All right, let's do. Should we do one of your homework problems? If you do your homework, then I should. Let's see if I could pick something that's similar to a homework that's not your homework. Is there a practice version? Let's see. I'll pretend to make up an assignment. Maybe I should do this for examples in class. Temp. We are in chapter 4, section Green's theorem.
Is that the same Green guy?
Yeah. Oh, it's not Green's theorem, it's Green function. Let's see. Oh, the answers are already here.
Yay.
So add that one.
Do that.
Add this one. Add this one. Oh, they look like some hard ones here. Wow, look at this one. They're all hard. All right, well, let's see. Update assignment.
Really? It says that's only 34 minutes? Really? That's not realistic.
So I think I have to assign this. I have to schedule it.
What if you did it on the 275?
What's today?
Because it's like two.
Okay. So now that we pretended to have another homework assignment, maybe I should give this for extra credit, huh?
Yes.
Instead of you don't go? Yeah, I know. Yeah, when somebody has a class on Wednesdays, you're pretty much screwed with that. I'll consider that. You don't want to write a paper instead? Because that was the other option. If you can't make it, you could write a paper.
We just do extra
Yeah.
problems and
Yeah, we'll see. We'll talk about it.
stuff. Just like one problem per paper.
All right, let's do some of these problems. It's going to take if it's going to take 34 minutes, then we should skip around.
Or you could subtract.
All right, let's start with number 2. From our temp problems. So we have a differential equation. This didn't have the whole initial conditions business, but we're still going to be forced to use the Green's function. And so for now, they want us to find Green's function. Actually, they want us to fill in this integral. And inside of the integral is not only Green's function, but it also is the f function. And I just have to be careful now, because I made that mistake, that this is a coefficient of 1. And so my f function is exactly this. But before I can go on, I still need to find out more information about Green's function. If you remember Green's function, we need to find y1, y2, and the Wronskian. So let's find y1, y2, and the Wronskian. So what we need to do is we need to find our auxiliary equation. And for this is not a Cauchy-Euler, so it's a little bit easier. M squared plus 8m plus 16 is equal to 0. And 4 twice. So m plus 4 quantity squared equals 0. So m is equal to negative 4 twice, multiplicity 2. So that gives us a y1 of, let's do the one without the x, so that's e to the negative 4x. And then y2 is going to give us x times e to the negative 4x. Okay? So now we need to find w, our Wronskian, which is the determinant of this thing, e to the negative 4x. And then we have x times e to the negative 4x. So this is e to the negative 4x times negative 4. And this one is going to be derivative of the first times the second, plus the first times the derivative of the second. And then we need to find the determinant. So I have e to the negative 4x times e to the negative 4x. That's e to the negative 8x. E to the negative 4x times this business. It's negative 4x e to the negative 8x. So that's the diagonal minus the product of the wings. I have negative 4 with a negative, so I'm just going to go ahead and call that positive 4x, and then multiply e to the negative 8x. So I think this simplifies a little bit. Oh, they cancel, right? So this is just e to the negative 8x. So that's your Wronskian. Yes, this is the one where if it's equal to 0, it's dependent. But you'll see in most of these, because the way we're finding our fundamental solutions, that these things are always never going to be dependent. Okay, so the formula. Some are x, some are t's, and so we need to figure out which one's which. Yeah, I don't remember. So why don't we just take a peek? Nope, it's not there. It's the one before. This is our magic formula. So y1 with a t, y2 with an x for the first one, and then you switch. Okay? So y1 with a t. So g of t function g of x and t, y1 with a t, I thought it was an x, e to the minus 4t, and then this one has an x times x e to the negative 4x minus, and then just switch the roles, e to the negative 4x times t e to the negative 4t divided by e to the negative 8t okay? So remember the Wronskian is going to be a function of t, so that's a function of t. And then now the f of t part is, if we take this thing and multiply it by f of t, then we're going to get the whole thing that's supposed to go inside of the integral. So f of t is equal to e to the negative 4t. So if I multiply that, I think I'm going to cancel. I'm going to get e to the negative 4x in the bottom, or e to the negative 4t in the bottom. So that's what I want to write here. Is there any simplifying that can happen? No. All right. So this is your y of p, and then the other thing that they want you to write down here is the general solution. So we have your y1 and your y2 already. So the thing that goes in here, I think, is just going to be c1 e to the negative 4x plus c2 x e to the negative 4x. Okay, and so fortunately they're not asking us to compute this antiderivative here. I don't think it would be that bad, but they're not asking us, so we're not going to do it. Yeah, you could break it up into smaller pieces, take out the things with an x in it, so you can have a nicer looking integral to deal with. All right, let's see how it's going to look like if I type that in. All right, the first one is going to be a fraction, a big fraction. on the numerator, it's going to be the x's first, right? X times e to the minus 4t, and then another e raised to the minus 4x. The next one is t, with essentially the same thing. And then the denominator is e raised to the negative 8xt. But I'm going to multiply this by the f of t function, which is e to the negative 4t, and then that would cancel 4 of the 8's here. So I think I can just put that down. And then the general solution, C1, e to the negative 4x plus C2 times x times e to the negative 4x. All right, looks good.
Can you show the formula for these, the IVD for these?
This thing. Oh, sorry. Let's just take a picture of it and carry it around with us. Let's put it here. Let's put it in our next page. All right, so let's do one that actually has an initial value problem.
So WT is the velocity,
Yeah.
and Z is like the target.
The F.
Okay.
All right, let's look at one that has a more complete setup or problem. Ooh, let's try number 3. This one should take 7 minutes. You remember? All right. So we have a non-homogeneous differential equation. It's a Cauchy-Euler one. So notice the x squared over there. So it's a little trickier. And if you remember the auxiliary equation, that might help move things a little faster. But this time we have initial conditions. Okay. So let's go through this. Let's march through this, see how quick we could do this. All right, so our auxiliary equation, if you have that memorized already, is equal to 1 times m squared plus, and then we have b minus a. There's no b here, so b is equal to 0 minus a is equal to 1. So that's a negative 1. M, and then C is equal to 6. So if you want to verify this, assume that your solution is y is equal to x to the m, and put x to the m into this differential equation by taking a couple of derivatives and then solving for m. So it looks like m minus 3 and m plus 2 would work. So this gives you an m that's positive 3, and this gives you an m that's negative 2. So you have two fundamental solutions. Y sub 1 is equal to x to the third power y sub 2 is equal to x to the negative 2 power, or 1 over x squared. Okay? So part of the theory says that we need to figure out our y is going to be y sub h plus y sub p. Y sub h is the solution to the homogeneous initial value problem using this. So let's figure out y sub h right now. By figuring out our initial value problem for the homogeneous differential equation. We're assuming that the right-hand side is 0 right now. So by the superposition principle, we're going to find our solution for this, y sub h, and then in the next step, we'll find yp. So what we need to do is we need to find our derivative. And the derivative here is negative 2 c2 x to the negative 3. And then we need to put 1 in. So when x is equal to 1, your original function will have c1 plus c2 equals to 1. And your derivative will be 3c1 minus 2c2 is equal to 2. And you have a couple of equations, a couple of unknowns. I would multiply the first one by 2 and then add it. So this would be 5 5c1 is equal to, I multiplied the top one by 2, and then I added it, so 2 plus 2 is 4. So c1 is equal to 4/5. c2 is equal to, if this is 4/5, then they have to add up to 1, so c2 must equal to 1/5. Okay? I hope that's all correct. So that's the first part. Now the second part, we have to find y sub p. According to our Green's formula, Green's function, our y sub p is equal to the integral from x sub 0 to x times Green's function times, or not times, the integral of Green's function times f of t dt from x naught to x. Now our x naught is 1, so that's going to be part of our initial condition, so it's important to put that down. I suppose we should try to figure out Green's function on the side here. G of x comma t is equal to it's equal to what's y1 again? X or t? T, right? T? T. So it's t cubed times x to the negative 2 power minus x cubed times t to the negative 2 power. We didn't do the Wronskian yet. Wronskian x squared, or x cubed, 3x squared, x to the negative 2, negative 2, x to the negative 3. So this is x cubed times x to the negative So this is going to give me a negative 2, right? Minus 3. Negative 5? Negative 5, that's it. Okay, now our f, remember we want to be careful with our f? Now we do. So our differential equation has an x squared leading coefficient, so we need to write our differential equation without the leading coefficient. So this is our f function. And then we're just going to make that a t. Oh, this is not looking good. All right, let's see how this is going to look like. Our x naught is 1. That's our initial condition. Our x is that. I have a negative 1/5. Let's see. What should we do with that? Let's write it separately. Negative 1/5. We'll take that out in a minute. The top part of Green's theorem is t cubed x to the negative 2 minus x cubed t to the negative 2 times f. Now the f, remember, you have to write as a function of t. So f as a function of t is going to be ln t divided by t squared dt. The 1? Oh, the integral is g of t. So the g, I got a negative 5 in the denominator. I just took that out. This thing became a 1 because of this. Whatever is in here. So if it's a 0, we put a 0 in. So they're either going to be 0 and 1. Those are the nice numbers that will come out. And then the top is always going to be x. No, these, when we do an initial condition, they're all the same. Now, there's another thing that says boundary condition where they're going to be different. And that's different. That's done differently. That's a different process. All right, let's see if this is going to be simplified. Any? So we'll break this up to two different integrals. One of them will have the t would cancel. We got t ln t. I think that's doable. And then there's an x in here. So I think what I'm going to do is I'm going to move the x outside. See this x over here? It's going to be outside. Because we're integrating with respect to t. Yeah. So the second integral, I took the 1/5 out already. I'm going to take the x cubed out as a constant with respect to t, going from 1 to x. And then I have t, this is going to be t to the negative 4, right? So both of these will require integration by parts. And so should we, just looking at the time. You could do it along the way, or I usually just finish the integral and then I plug in the limits.
Okay, so you do the limits at the very end.
Yeah.
Once you've integrated the second part of it.
Yeah. So let's integrate t times log of t Well, what if we just stop here for now and then we'll continue the rest tomorrow or on Thursday? So it took more than 7 minutes, huh?
So the homework that you did,
Yeah. All right, we'll come back to this next time after we take our quiz.
we have a quiz on Thursday?
Yeah.